Let's continue our work with this language. Let's first show that this language is not regular using pumping lemma. Remember that we need to pick a special string s. In this case, let's pick our string s to be 0 to the p, 1, 0 to the p, where p is the pumping length. We can see that the string s is inside the language and its length is greater than or equal to p, so we can use this string in our proof. For any partition of this string s into 3, x, y, z, assuming that conditions 2 and 3 of the pumping lemma hold, that is, assuming length of y is greater than 0, second condition, and length of x and y together is less than or equal to p, we need to show that there exists I such that x, y to the I, z does not belong to the language. If we can do this, then we are done with our proof that this language is not regular. If we visualize the string s, it contains p many zeros at the beginning, followed by a single one, followed by p many zeros. So we have p many zeros at the beginning here, and p many zeros at the end in here. As usual, if we try to locate where this is our string x, y, z partitioned into 3. If we try to locate this middle string y, due to this condition that xy, length of xy is less than or equal to p, this means that the two strings x, y together, they lie within this range. So they don't extend further, which means that y can be anywhere in here. Y is anywhere in this range, anywhere here, and we know that y is not epsilon. Now let's consider a new string x, y squared z, for instance. How does it look like? We'll have a bunch of zeros followed by a single one followed by a bunch of zeros. Since y lies among the first part of the zeros, and we are repeating y twice in our new string, this means that the number of zeros at the beginning must have increased. Now we know that there are more than p zeros in this range. Furthermore, the number of zeros at the end remains p because y doesn't extend to this part, so this part is not modified in the string. Now if we take a look at this string, it consists of more than p zeros at the beginning, followed by a single one, followed by exactly p zeros at the end. Now such a string is not a palindrome anymore, because reading such a string from left to right is not the same as reading the string from right to left. Reading the string from left to right, we will encounter the symbol 1 at some location greater than p, whereas reading the string from right to left, we will encounter the symbol 1 at some location exactly equal to p plus 1. So reading the string from left to right is not the same as reading the string from right to left. X, y squared z is not a palindrome. Therefore, x, y squared z does not belong to the language L, which further implies that the language L is not regular. We know that this language is not regular. Now, naturally, the next question that comes up is the language context-free? To see this, we will try to see whether we can design a context-free grammar that generates such a language L. So, can we design a context-free grammar G such that language of the grammar G is equal to this language L. How to design such a grammar? While designing context-free grammars, again, we will make heavy use of induction. So let's start with our starting variable s. Assuming that the variable s is capable of generating any string inside this language, basically any string that is a palindrome. How can we extend such strings to have larger length? That's the main idea. So assuming s already is capable of generating a short palindrome, how can we generate such a short palindrome to get a longer sequence? If you want to visualize a string w that belongs to this language, it might be of the following format. If the string w starts with a 0, it must be the case that it ends with a 0 as well. And in between, whatever we have must also be a palindrome. So if w starts with a 0, since w is a palindrome, it has to end with a 0. Furthermore, whatever is in between must also be a palindrome, w prime. Okay? So if this is the case, it's easy to see that if s is capable of generating shorter palindromes like w prime, then I can easily write a rule to generate a longer palindrome w. Okay? So for such a case, I can write a rule that says starts with a 0 and then generate a string using the rules of s that corresponds to this w prime, which already is also a palindrome but a shorter palindrome. So 0s followed by 0. Assuming s is already capable of generating any shorter palindrome, 0s0 will generate a palindrome, a longer palindrome that starts with 0. Another case could be that w starts with a 1. If this is the case, and if w is a palindrome, it has to end with a 1. Furthermore, whatever is in between w prime should also be a palindrome, should also belong to the language. But now it's easier to generate such strings because we know that w prime can be generated by the grammar s. So to be able to generate all such strings, we will write down the following rule. Start with 1. Generate a string already in s that is a palindrome that is shorter, and then followed by a 1. Now note that these two cases, string w starting with a 0 or string w starting with a 1, covers all possible cases. Okay? Now these will be the two production rules that corresponds to an inductive step that is usually seen in the inductive proofs. But remember that for the inductive proofs, we have another component, which is the base case component. So it's the same for our grammar as well. We have written down the rules that correspond to our inductive parts of our proofs or inductive creations. Now we need to write down rules that correspond to the base case. For the base cases, we will try to think of the shortest possible strings w that belong to the language. So w can be epsilon. Epsilon belongs to the language, it's a palindrome, and its length is 0. So I will write down a rule that corresponds to this base case. So s goes to epsilon is another production rule. Are we done yet? So if we only had these three rules, then s could generate the string epsilon, or it could generate the string, for instance, 0, 0 by replacing s with epsilon, or it could generate the string 1, 1, or longer strings. What is missing is strings of length 1, because this generates string of length 0, that is a palindrome. These two generate strings of length at least 2 that are palindromes, but strings of length 1 that are palindromes cannot be generated only using these 3 rules. So we need further base cases. We need W being equal to simply 0, because this is also a palindrome, and we need W equals to 1 as yet another base case. So these correspond to our base cases, and these correspond to our inductive generations. So we need to write 2 separate rules as well. S generates also 0, or S generates 1. All these 5 production rules all together gives us our grammar G, and this is the grammar that generates this language, or in other words, this is the grammar that generates all palindromes that are strings of zeros and ones. Let's consider yet another example. Let's say we define the string L as, again, a string of zeros and ones, such that this time let's say length of W is odd and middle symbol of W is 0. Middle symbol is 0. How can we design a context-free grammar that will generate this language L? Okay, let's try to think of the same methodology. So let's say we have our string W. Now, if W starts with a 0, what are the possible cases? What can we have for the remaining part? You should be able to notice that if W starts with a 0, W may end with a 1, and we have something in between. What is the property that we would want from this middle string? We would want this one to have exactly the same property as defined by the language. That is, if this is W prime, we want W prime to have odd length and its symbol to be 0 as well, so that the string W itself has odd length and its middle symbol is 0. Okay, but we can have also W starting with 0 and ending with 0, and for the middle string W prime, again we would require the same property, that this middle string has odd length and its middle symbol is 0. These are the 2 cases where, let's say case 1, W starts with 0. Case 2, W starts with a 1. If W starts with a 1, again, it will be followed by some string, and it may end with a 1, or starts with 1 followed by some string and ends with 0. But what is it that we expect from the middle string? We want this middle string W prime to have, again, exactly the same property. So we want W prime to be inside the language L as well. Same goes here. If W is to be inside this language, then W prime in here, in the middle string W prime, should belong to the language as well. That is, its length should be odd and its middle symbol should be 0. Otherwise, we couldn't have W to be in the language. Now, these actually 2 cases, or 4 considering the subcases as well, all these 4 cases actually correspond to the inductive part of our generational rules. Again, we need to provide rules correspond to the base case. For the base cases, remember we were trying to consider the simplest or the shortest possible strings. The shortest possible string that we can have inside this language L is W being equal to simply 0. Because just a string that consists of a single 0, its middle symbol is 0 and its length is odd. So both these properties are satisfied, and this is inside our language L. Now this corresponds to the base case of our construction, basis. Now that we can see that we have been able to generate strings belonging to this language using the principles of induction, let's now turn these principles of induction into concrete rules of a context-free grammar. Let's now write down our context-free grammar. Our starting variable s. Now, for the rules that will generate strings of this form, starting with 0 and ending with 1, in the middle, as we said, we need a W prime, a shorter string that belongs to the language. So a shorter string that belongs to the language can be generated with s itself, because by induction we can safely assume that s in here is capable of generating all strings in this language that have length smaller than this current string. So this rule will generate all strings of this form. We also need a rule to generate strings of this form. 0, s again will generate strings W prime that has the same property but that are shorter than the whole string. We need a rule for this case, 1s1. We need a rule for this case, 1s0. Finally, we need a rule for our base case, which is simply 0. So this grammar generates the given language L. Again, to formally prove that that is the case, we can use induction. Just as we use induction while designing our grammar, we can use to prove that our grammar corresponds to the language or our grammar generates the language, we can again use induction. But I will not show the steps of that proof. Let's consider yet another example. Let's say that W consists of zeros and ones, again, such that W has equal number of zeros and ones. So for instance, W equal to 0, 1, 0, 0, 1, 1 would be inside the language because the string W has 3 zeros and 3 ones. In this case, for this language, the order of zeros and ones do not matter, as long as in W the number of zeros is equal to number of ones. Now the question is, can we design a context-free grammar G that will generate such a language L. Again, let's think in terms of induction to design such a grammar. So let's say that we have a W in L in this language that starts with a 0. Again, as this is the inductive part of our construction, W, we will split it into two cases. W starts with a 0 or W starts with a 1. Let's consider the case where W starts with a 0. What can it be followed by this 0 so that the string W is inside the language? So since we want the string W to belong to the language, if 0 is followed by some string W prime, what is the property that we expect from this W prime? The property that we expect from W prime is that number of ones should be one more than the number of zeros. Number of zeros plus 1. This is the property that we want from this string W prime. Okay. If on the other hand W starts with a 1, it will be followed by some string W prime. What is the property that we want from this W prime? We want this time just the opposite. Number of zeros in here in W prime to be one more than the number of ones. Number of ones plus 1. Now, how can we achieve the given the string W prime by only using the production rules of S? Or before going into that, let's try to complete. So these are the inductive parts of our construction. Let's complete our construction based on induction by providing the base case as well. So what would be the shortest string W that belongs to this language? W is equal to epsilon. It has length 0 and it's basically the empty string. The number of zeros in this string is equal to the number of ones, both of which are zeros. So this is the base case of our construction. This is the base case. And these two are the inductive portions of our construction. Now the question will be, can we generate rules, production rules corresponding to each of these cases? Let's start with our starting variable S. The base case is easy. We can have a rule that simply generates the string epsilon. Now, for the inductive portions of our design, to be able to generate all strings of W that start with 0 and that belongs to this language, so we have a 0, and 0 should be followed by W prime. The property of W prime is that number of ones should be one more than the number of zeros. Now the crucial question will be, how can we describe this W prime in terms of S itself? Since we are using the principle of induction, that will be the question. Now W prime can be generated by the following string: S followed by a 1 followed by an S. Okay, why? This string S1S will generate all strings that are in this format, that have the number of ones being one more than the number of zeros, since S itself contains strings with equal number of zeros and ones. Okay. Why did we write down S before and after the symbol 1? Because we want to generate all such strings with one more one than the zeros. Okay, because S is general enough so that it can start with anything and the string can end with anything. Okay, in order to do the same thing for the next type of construction, to be able to generate all strings belonging to the language that start with the symbol 1, what should it be followed by? We can write down S0S. Note that again, this string in here will generate all strings that have one more zero than the number of ones, assuming that S is capable of generating all shorter strings belonging to this language. Okay. With this, now again, with these three production rules, we have our grammar G such that the language generated by this grammar G is exactly the same as this language L. Let's consider one last example that is going to be very similar in terms of its definition. Again, WN01 star, such that this time, let's say we want strings that contain more ones than zeros. W has more ones than zeros. Again, let's try to think of in terms of induction. The base case, for the base case, what could be the simplest or the shortest string that belongs to this language? For the base case of our construction, W equals 1 is the shortest string that belongs to this language because it has more ones than zeros and it has length 1. For the inductive part of our construction, again, we will assume that we can easily construct all strings that belong to this language with certain length. And the idea will be, how can we take those strings and extend them further for the inductive part. Let's take a string W that belongs to this language. W may start with a 0 or may start with a 1. Let's consider the case where W starts with a 0. If W starts with a 0 and is followed by some string W prime, what is the property that we want from this W prime? The property that we want is that in W prime there are at least 2 more ones than zeros. 2 more, at least 2 more ones than zeros, because there already exists an existing 0 in W. So in W prime we have to have at least 2 more ones than zeros. Okay, and while writing down the rules, the production rules for the grammar generating L, the goal will be, how can we define W prime in terms of the variables that are employed in our grammar. So this is one case, and the second case is W may start with a 1. If W starts with a 1 followed by a string W prime, what is the property that we need from this W prime? Well, there are two cases for W prime. Both of them will make W belong to the language. W prime may have equal number of zeros and ones, equal number of zeros and ones, because if we have equal number of zeros and ones in W prime, then in the whole string W, number of ones will be more than number of zeros, or more W prime has more ones than zeros. Now let's see if we can write down production rules such that we will be able to generate all strings in L corresponding to each of these cases. Let's start with our starting variable s. Corresponding to the base case, we'll have a production rule that says s generates the string 1. Okay. Next, let's see if we can generate all strings corresponding to this case. So we need to write a rule that generates all such strings. The string starts with a 0 and it's followed by some string W prime, such that in W prime number of ones is at least 2 more than the number of zeros. Can we describe such a W prime with the strings that can be generated through S? We cannot generate it directly because S generates all strings such that strings have more ones than zeros, but we want in W prime we want at least 2 more ones than zeros. So if we simply just write one S in here, it will not suffice, because it might be the case that S has only 1 more ones than zeros. If that were the case, 0S would have equal number of zeros and ones. But what we can do is we can add yet another string S afterwards, so that we get a rule that says 0SS. In this string now we can see that this string S and S followed by S generates all such strings W prime, because in S itself there's at least 1 more ones than zeros. Again, in S itself there's at least 1 more ones than zeros. So in S and S combined there's at least 2 more ones than zeros, which tells us that in the string 0SS we will be able to generate all such strings W that belong to the language and that start with a 0. Now, to generate all such strings that belong to the language and that start with a 1, so we start with a 1. Remember that there were two cases. W prime can have equal number of zeros and ones, or in W prime we can have more ones than zeros. Let's first concentrate on this one. How can we generate all such strings starting with 1 and W prime has equal number of ones and zeros? Note that in terms of S, we don't have any definition in terms of equal number of zeros and ones. But if you remember from the previous example, we exactly created the grammar that generates exactly those strings. This grammar in here generates the language where all strings have equal number of zeros and ones. Okay? So we can actually make use of the grammar in here. But this S in here, we should not confuse it with the S in our new grammar. So therefore, the previous grammar, let's use the variable E to start that grammar. E could go to epsilon or 0E, 1E, or 1E, 0E. Note that This set of rules is exactly the same as the previous grammar. The only difference is that S is replaced with E. So we know that in this new grammar, E is capable of generating all strings of zeros and ones such that number of zeros is equal to number of ones. And that's exactly what we need for strings of this format, where the string starts with a 1 followed by W prime, where in W prime we have equal number of zeros and ones. So this handles the first case. To create a rule that corresponds to the second case, our string starts with a 1. It should be followed by some string that contains more ones than zeros, but this is exactly the same as the definition of our language, and in other words, it's the same as S. So 1 followed by S. Okay. So base case generated through this first rule. For the inductive part of our design, cases of the following sort where the string starts with a 0 will be generated through this rule, and strings starting with a 1 can be generated either through this rule corresponding to this case or this rule corresponding to this second subcase.